Okay, fifth graders, your homework tonight is a lot like we worked on in class. We just didn't give them all these fancy names, so I'm sorry. I was going to have you bring home your SRB, but I forgot to ask you to do that, so hopefully this video is going to be helpful for you. Let's read some of the directions up here. It says a flat surface of a geometric solid is called its face. You can see the face just like we were talking about today and we did yesterday too. A corner of a geometric solid is called its vertex, and you can see where those points are. Notice they changed it to vertices. If we have one, we call it a vertex. If we have more than one, we call them vertices. The edge of a geometric solid is a line segment or a curve where the two surfaces meet. So you can see the line segments here. And in this book series, even if it has a curve, it's still considered an edge. Polyhedron is just a name for a three-dimensional shape. First one we start with is the cube. Here's an example of a cube. And just like we talked about in class, the faces are those flat things, the flat surfaces, and we can count the base, 1, and then the top, another base, 2, 3, 4, 5, 6. We get 6 faces. The vertices then are those points, 1, 2, 3, 4, flip it over, 5, 6, 7, 8. And then add those two together. I think we'll come up with a formula here. 6 plus 8 is 14. Next we need to count the edges. 1, 2, 3, 4. We know we're going to have the same on the other side. 5, 6, 7, 8. So we've got those two. 8, 9, 10, 11, and 12. Did I count them all? Yes, 12 edges. The next one is a tetrahedron. A tetrahedron has all equilateral triangles. So when we talk about number of faces, we've got 1 on this side, 2, 3, plus the base makes it 4. So 4 faces. Vertices, the points, we've got 1, 2, 3, plus the one at the top is 4. We're going to add those two together. 4 plus 4 equals 8. And then we want our edges. How many edges? 1, 2, 3, 4, 5, 6. We get 6 edges on that one. Okay, the next one is an octahedron. I put it off to the side of the screen here because it's not a shape that I have, but you can see right here what an octahedron looks like. And if I count on the octahedron how many faces, I see 1, 2, 3, 4 on the top, 1, 2, and 3 at the back, 3 and 4, another 4 on the bottom half of it. So a total of 8 faces on that one. And then vertices, those are the points. I can count 1, 2, 3, 4, 5, and then another one down here, kind of got cut off, would make it 6. And then I've got 8 plus 6 is going to equal 14. And then number of edges, if I count just the edges. 1, 2, 3, 4, right here in the middle. 5, 6, 7, 8, 9, 10, 11, 12. So I get 12 edges on that one. Okay, the dodecahedron is this fun looking one down here. It looks a little like a soccer ball, but we'll count the number of faces on that one. Whew, that's going to be a challenge. Let's see, I've got 1 here and 1 here at the bottom. That would be 2. And then I've got 3, and then the other side 4, 5, and its other side 6, 7, and its other side 8, 9, and its other side would be 10. Did I get them all yet? Nope. This one 11, and its other side would make it 12. So on a dodecahedron we have 12 faces. And then vertices, that's points. Yikes, I'm going to have a bunch. 1, 2, 3, 4, 5. And then the bottom side's going to have another 5. So 5 and 5 is 10. And this one, 1, 2, 3, 4, 5, and its other side is going to have 10. So we've got 5. We've got, let's try again. Each time I see this, I'm doubling it. 5, and then that one will be 10. 15, and its other side would make it 20. This one, 25, 30, 35, 40, 45, 50. Did I count that right? Dodecahedron. I think I've got too many. 1, 2, 3, 4, 5, 6. Oh my. You know why? Look at how many. Some of these are pentagons. This one happens to be a hexagon. 1, 2, 3, 4, 5, 6. So 6 points on that one. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And then 18, I'm lost, 18, 19, and 20. And I'm just going to say we have 20. I'm not sure if I got it right. I'd like to pick it up in my hand and move it around, but I know the book tells me we really truly do have 20. If I could pick it up and look, I'm sure we'd be able to get it. 12 plus 20 is going to equal 32. Number of edges. Edges. Okay. The edges. Here we go with our 5. 5, and then the other side is 10, 15, 20, 25, 30. We should have, when we're done, 30 edges on the dodecahedron. And then our last one, moved on down here, isosahedron. Yikes. And that one, we need to count how many faces there are. I'm counting 1, 2, 3, 4, 5. And then down here would make it another 5, so 10, 11, 12, 13, 14, 15, 16, 17, 18. I think I might have missed some because I'm supposed to have 20 once all is said and done. So maybe if you count it, you'll get 20. I got lost in there and got 18. And then vertices, those are their points on it. 1, 2, 3, 4, 5. And then down here, another 5. That makes it 10, 11, 12 for vertices. And we can add 20 plus 12, and we get, ironically enough, 32, just like the one above it. And now we need to count number of edges. Are you noticing a pattern here, 5th graders? 14 was their total, and then edges was 12. 8 and 6, 14 and 12, 32 and 30. What seems to be happening? Are you notice that it seems to be reduced by 2? Faces plus vertices, subtract 2. Face plus face plus vertices, subtract 2. Face plus vertices, subtract 2. Face plus vertices, subtract 2. So my prediction is this is going to be 30, which would make it so much easier to count than actually trying to count on the picture. But we'll try with the edges. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to count at this. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. I got 28. I must have missed a couple because the book says I should have gotten 30 if I counted right. Now it is asking us to come up with a formula for this one. It says compare the value of the faces plus the bases in this column with the number of edges, and we came up with that little plan there. If you add faces plus the vertices and subtract 2, you will get the number of edges. Okay, I'm going to fold this down so I can move it up a little easier. It says 2 of the patterns below can be folded to make a tetrahedron. If you remember, this is what a tetrahedron would look like. It's a pyramid, it's a triangular pyramid with all sides exactly the same. So 2 of the patterns below can be folded to make a tetrahedron. Cross out the patterns that will not make a tetrahedron, and then circle the pattern that will make a tetrahedron. Explain your strategies for solving it. So we got to do a little imagining with that one. If I folded it right here, that paper right here, and I folded it again here and here, could I fold it into something that would make a tetrahedron? The answer is yes, I could do that one. This one, it seems like I could fold it. The only problem is I think I'm going to have too many sides. 1, 2, 3, I'd have 4 sides, and a tetrahedron only has 3 sides, so that one's not going to work. This one, I was able to fold one under to be the base. This one I can't. I can't do that for the base. This one I think I could. If I could make this one right here the base, then I could fold these up. I could make that into a tetrahedron. This one right here, I think I just might have too many faces altogether. If you recall, a tetrahedron was supposed to have 4 faces. And when I look at this, I've got 1, 2, 3, 4, 5. I've got 5 faces, so that one's not going to work. Okay, 2 of the patterns below can be folded to make a tetrahedron. We found them. Cross out the patterns that would not make a tetrahedron. Circle the patterns that will make it, and explain your solution. Well, we eliminated that one. Let's see. It needed to have 4 bases, so that one is going to get eliminated. It needed 4 faces. It also needed to be folded in a way that would give us a base. Okay, so it needed to have 4 faces, so that eliminated that one, and then this one we couldn't fold it in a way that would make a base, so that one won't work for that reason. Alright, thanks so much for working with me today.